Hello everyone, my name is Zhuoran Song, and I am a PhD student from Shanghai Jiao Tong University. It's my pleasure to report our research, namely VR-DANN, real-time video recognition via decoder-assisted neural network acceleration. Today, I will talk about the following points one by one. As we all know, video recognition tasks mainly include segmentation and detection. Those tasks can be applied to the following applications. Recently, many works propose to design deep neural network to chase high accuracy, but the computation time and energy sharply increase. Some massive works propose to accelerate VR tasks, but we can see in the figure, the speed is still far from real time. For example, the classic ovals and favors algorithm feed the deep neural network on a frame-by-frame process for feature recognition. However, the frame-level schemes are quite slow. Aiming for faster video recognition, researchers try to reduce neural network workload by not fully processing every frame. Those works first distinguish key and non-key frame by a fixed interval, and then differentiate the temporal information between key and non-key frames. They can skip part of computations of non-key frames using the temporal information. But the overhead of obtaining the temporal information is large. Moreover, they select the key and non-key frames with an arbitrary interval, which can lead to unacceptable accuracy loss. Most importantly, the existing work lack of exploration on video expertise. Due to the limited network bandwidth, online videos are usually encoded and compressed by video encoder. During the encoding process, the video frames are classified by IPB frames. For consumer devices, they decode the video into normal frames by video decoder, and B frames are reconstructed by I and P frames. During video segmentation task, the segmentation results are generated by large neural network, but such scheme has significant cost. To reduce the overhead of video recognition, we wonder, can segmentation result of B frame also be reconstructed? As shown in the figure, the segmentation result of B frames can be reconstructed using the reference segmentation result. In the following, we introduce our proposed VR-DANN algorithm in detail. We first locate and retrieve the reference segmentation result using source X and source Y coordinates. Then, we can place the result to the destination of B frame according to dest X and dest Y coordinates. Those coordinates are recorded in the motion vector table. Note that the coordinates are quite random, which may complicate the memory access pattern or the fine-grained memory control, as we will discuss later. However, since our scheme is applied per macroblock basis, the identified object bears unacceptable noise for real application. We therefore propose to refine the reconstruction result. In short, there are three major challenges of our proposed VR-DANN. The first challenge is how to guarantee the accuracy of video recognition. We build a small neural network to refine the reconstruction result. The second challenge is how to enable the proposed flow in the existing hardware. We design a serial VR-DANN algorithm flow to enable the proposed flow. The last challenge is how to support efficient VR-DANN algorithm. We propose a standalone VR-DANN agent unit that can work with any third-party IP. Moreover, we reschedule large and small neural network execution order to reduce the kernel switching overhead. In addition, we also parallelize reconstruction and reschedule the motion vectors to speed up the reconstruction process. We will discuss these challenges in the following. For the first challenge, we build a three-layer convolution neural network. The input of our proposed small network is a sandwich-like three-channel input. The middle channel is a reconstruction result of B frames. The first and the third channel are the intermediate preceding and the following segmentation results of the reference I and P frame. To train the small neural network, we fully decode the training dataset for I, B, P frames. and obtain the motion vector of B frames. The I and P ground truths with the motion vector in the B frames are used to reconstruct the reconstruction result, which are then combined with the ground truth I, P frames as a sandwich image. Finally, we use the sandwich image as the input, and the B ground truth as a label to train the small neural network. As the structure of the small network is much smaller than the large network, the training overhead of the small network is negligible compared with the large network. To enable the proposed flow in the existing hardware, we can first execute large neural network using NPU. Then we execute reconstruction of B1 frame. After that, we execute small neural network of B1 frame using NPU. We repeat executing reconstruction and small neural network of B frames. And we repeat the above process to finish our proposed algorithm. However, the total serial VR-DANN algorithm incurs frequent kernel and weight switching. In addition, the reconstruction is executed serially. Last but not least, the reconstruction costs random memory access. Those limitations cause performance degradation. Therefore, we propose a VR-DANN architecture to support efficient VR-DANN algorithm. The above figure shows the third-party IPs, including video decoder and NPU. NPU is used to enable neural networks. To cooperate with the third-party IPs, we propose a standalone VR-DANN agent unit. We can use it to control neural network and reconstruction order, and therefore to enable parallelized and efficient reconstruction. Inside the agent unit, the motion vector table is used to provide motion vectors of B frames, so that the reconstruction process can be parallelized with neural network execution process. As shown in the below figure, the execution time can be reduced when we parallelize the reconstruction process. Moreover, we equip two independent queues to reschedule large and small neural network execution order and to keep a stable NPU mode as long as possible. In this example, the queues change the segmentation order with only one kernel switching. Moreover, we utilize the on-chip buffers and the coalescing unit to reschedule the motion vectors, so that the time consuming of reconstruction is reduced compared with serial scheme. Specifically, we can find that one reference block can reconstruct multiple blocks simultaneously. This opportunity naturally leads us to coalesce multiple blocks in one single DRAM burst request. We now explain the motion vector rescheduling by taking the example in the figure. Suppose the motion vector table has 8 motion vectors, and they all point to some reference block in an iframe. We design a coalescing unit to generate memory requests with address indexed from ref and source Y fields in the motion vector table. In the example, we first consider the reference index and source Y fields as 0 and 11. We send the coalesced memory request to DRAM. Once the request is returned, we can reconstruct 2 blocks simultaneously. To validate the accuracy of our proposed algorithm, we test on segmentation dataset Davis and detection dataset ImageNet. We compare the accuracy, performance, and energy with several accelerators. OVOS is a classic method targeting video segmentation. Favors and Salsa are the state-of-the-art methods targeting video segmentation and detection respectively. Both methods apply large neural network on each frame. Aiming for faster video recognition, DFF and iframes utilize the temporal information between frames so as to skip part of computations. Different from those accelerators, our proposed VR-DANN seeks the temporal spatial information across frames by the video encoder. Those information has well exploited in the recent generation of video encoding standards, such as 264 and 265, and we model our proposed architecture by simulation. Let's see the accuracy of all techniques first. Compared with others, VR-DANN increased F-score and IOU by 5.5% and 7.6%. Compared with DFF, F-score and IOU increased 3.3 and 3.8%. And compared with favors, F-score and IOU only decreased less than 0.4 and 0.5%. Similarly, for detection task, our proposed algorithm decreased only 0.8% MAP compared with CELSA. And compared with ePhrase2, MAP even increased 0.1% with 40% enhanced performance. When compared with ePhrase4, MAP increased 5.6%. Due to the capability of leveraging the precise motion vectors that are extracted by codec, our method outperforms other techniques on accuracy. For performance, compared with others, DFF, and favors, the serial execution of our proposed algorithm increased 3.9, 2, and 1.5 times respectively. This is because our proposed algorithm can reduce a significant number of frames passing through the large neural network for segmentation. To further accelerate our proposed scheme, we designed the VR-DANN architecture, and our architecture can further improve the performance by 1.5 times. With the help of the standalone agent IP, our architecture can achieve highest performance speedup. In detail, compared with favors, performance of our VR-DANN varies across different videos. For example, VR-DANN improved 4.2 times on cows, 1.6 times on Libby, and the TOPS drops 16% on average. For energy saving, our proposed architecture can reduce 4.3, 2.1, 1.7, and 1.1 times compared with other techniques. Our proposed architecture saves memory energy due to the dedicated memory coalescing scheme, and it reduces the NPU switching costs thanks to the independent queuing scheme. There could be several factors that impact the accuracy and performance from the video encoding scheme. We first explore the impact of B-frame ratio. We can see that F-score and IOU suffer more accuracy drop at higher B-frame ratio, while performance improves with increased B-frame ratio. This is understandable, because the more B-frames are, the more likely we can leverage the advantage of the codec for speeding up. Our proposed architecture works well with the auto-tuned encoder, yielding both accuracy and performance. We also explore the video encoding standards. We find that H.265 generally delivers better accuracy than its peer generation. This is because H.265 applies a more flexible motion prediction algorithm and a finer grain macro block size, at the cost of higher computing requirement on the more complicated encoder hardware. In conclusion, we propose a novel decoder-assisted video recognition algorithm so that we can fast reconstruct and refine B-frames. We also propose an efficient decoder-assisted video recognition architecture to accelerate our VOR algorithm. By rescheduling neural network execution order, parallelizing reconstruction, and coalescing memory requests, we can achieve higher performance improvement. Our proposed VR-DANN can keep high accuracy while gaining large performance improvement. That's all. Thanks for your attention.